Okay, let's get right into it. Welcome to this explainer. If you're gearing up for your dental boards, or, maybe just looking to really bulletproof your clinical knowledge, you've landed in the exact right spot. Think of this as your ultimate high-yield masterclass on root canal adhesion, completely based on the foundational research of Professor ABEER A. El-Hakim El-Jendi. We're going to distill this right down to exactly what you need to know, and I promise you, literally zero high-yield facts are getting left behind today. So, let's dive in. Here's our syllabus for today. We're hitting 1. The basics of adhesion. 2. Defeating microorganisms. 3. Bacterial entombment. 4. The evolution of materials. 5. Root canal anatomy limitations. And 6. The absolute lifesaver, our chemical interactions cheat sheet. Starting right off with Section 1. The basics of adhesion, defining the mechanism.
Look, these foundational definitions, they're absolutely guaranteed points on your exam if you know them cold. And let's be real, we all need those easy points to balance out board prep anxiety, right? So lock this one into your memory. According to Davidson in 1996, adhesion is strictly defined as, quote, the mechanism that bonds two materials in intimate contact across an interface. Now, how do we actually get that intimate contact? Well, the source identifies 3 distinct pathways, and you've got to know all 3. We're talking chemical adhesion, physical adhesion, and mechanical adhesion. If you see a multiple choice question asking for the primary mechanisms of bonding in an interface, boom, those are your 3 targets.
Moving on to Section 2, defeating microorganisms, the main culprits.
So now that we know what adhesion is, we really need to understand what threatens it. We're focusing heavily on the specific biological threats that lead to pulpitis, apical periodontitis, and ultimately total treatment failure. According to Secura's research, since completely scrubbing out every single microorganism before obturation is, well, practically impossible, we have to know exactly who our main enemies are. I want you to lock these 4 specific bacteria into your brain right now. Ready? Enterococcus, Fusobacterium, Probrionystinithium, and Actinomyces. I'm calling this out explicitly because, guys, they are classic multiple-choice distractors. Exam writers absolutely love to mix these up with other oral bacteria. You just need to recognize these 4 as the main culprits responsible for root canal failures.
Section 3. The bacterial entombment concept, sealing the enemy. Since we literally just established that 100% microbial eradication isn't really on the table, what's the actual clinical objective of modern endodontics? Well, the whole crucial point is captured beautifully right here. Our aim is to overcome the limits of chemomechanical prep. The goal is to eliminate the space and completely seal within the root canal system any irritant that can't be fully eliminated. This is formally known as the bacterial entombment concept. It's a huge conceptual anchor. You're not just filling a hole. You are actively entombing those pathogens we just talked about, essentially locking them away from the periapical tissues for good.
All right, Section 4, Evolution of Adhesive Materials, Historical Benchmarks.
Whatever you do, please don't skip the history. Chronological benchmarks are prime testing material because they prove you actually understand why we use the materials we do today. Let's trace this lineage really quick. The big breakthrough started way back in 1938 when Gaston invented epoxy resin. That eventually sparked the early era of tossing resin into root canal sealers, most famously with AH26. But, actually, AH26 was far from perfect, and that directly paved the way for our modern era. AH Plus was specifically designed to fix the exact problems associated with AH26. So, if you get a sequencing question, it goes Gaston's 1938 epoxy to AH26, evolving directly into AH Plus as the ultimate problem solver.
Section 5. Root canal anatomy limitations. What stands in the way?
Exams absolutely love testing the physical variables that mess with bonding in the canal. Just take a look at this Venn diagram straight from the source material. The limitations of bonding to dentin do not happen in a vacuum. Failure isn't just, oh, I picked a bad material. The true limitation happens right at the messy intersection of anatomy, material, and technique. You need all 3 of those working in total harmony. If your technique is completely flawless, but the local anatomy is compromised, your bond is totally compromised.
Let's connect all that abstract theory to physical reality. Look at this microscopic view of the dentinal tubules and the interface itself. Just think about what we're physically up against inside that canal. We're constantly fighting the highly variable number of dentinal tubules and the sheer thickness of the dentin. We're battling literal physical barriers, accessory canals, pulp stones, areas of root resorption, and of course, those notoriously frustrating, untouched areas that just somehow escape shaping. Honestly, the absolute bane of every dental student's existence, right? These are literal physical roadblocks stopping that intimate interfacial contact we defined earlier. Building on those anatomical limits, we've got our high-yield material and biological limitations. I want you to pay very, very close attention here. You absolutely must know about polymerization shrinkage and how the resin bond deteriorates over time. But I want to heavily emphasize two specific things: the configuration factor, or CF, and matrix metalloproteinases, known as MMPs. I can practically guarantee you're going to see a question trying to trip you up on how the CF, or the presence of MMPs, alongside bacterial enzymes, totally limits dentin bonding. Seriously, underline those in your notes right now.
And finally, Section 6, Chemical Interactions Cheat Sheet, Irrigants and Bond Strength.
Guys, this is the absolute climax of this explainer. This is your ultimate cheat sheet for chemical interactions, covering exactly how our irrigation and medication choices dictate our bond strength. First up, we've got to contrast EDTA and chlorhexidine. Both are used and both actually remove the smear layer. But here is the classic trap they set for students. EDTA removes the smear layer and does not affect the mechanical properties of the dentin. Chlorhexidine, on the other hand, removes the smear layer, but it actually degrades the dentin's mechanical properties. If an exam asks which one compromises mechanical integrity while stripping that smear layer, your answer, without a doubt, is chlorhexidine.
Okay, this chemical interaction matrix, it's a screenshot-worthy goldmine for your boards. Let's rapid fire through this. Sodium hypochlorite, it leaves an oxygen-rich layer which actually decreases bond strength. Hydrogen peroxide, totally safe, no loss of bond strength. Chloroform, be super careful there, it decreases bond strength dramatically. What about eugenol? That one directly inhibits polymerization. Calcium hydroxide, it acts as a physical barrier. Plus, its alkaline pH literally neutralizes the acidity of your acid edge. And lastly, Carey's detector, absolutely zero effect on bond strength. Memorize these specific interactions. They are the exact tiny details examiners use to separate the truly prepared students from the ones who are just guessing.
So, we've defined adhesion, we've named our bacterial enemies, traced the whole history back to AH+, and basically mapped out the physical and chemical minefields of the root canal system. I want to end today by pushing you out of just rote memorization and into an active clinical problem-solving mindset. Knowing the microscopic anatomical hurdles and the exact chemical interactions we just walked through, how will you actively overcome the configuration factor and polymerization shrinkage when you step into the clinic for your very next root canal case? Keep that question front and center as you study. Thanks so much for joining me for this explainer, and stay curious.